So if a continuous random variable is distributed in the exponential distribution, it follows a density function that is right skewed. So it's as if your right hand is pulling the density. And this is a non-symmetric distribution. The exponential distribution is good for modeling things like failure times. And it's nice because it has an easy formula for its CDF. But this non-symmetric distribution isn't very useful in situations when you want a symmetric distribution. So today we come up with a model for a symmetric probability density function. Essentially what we're going to come up with is something that's known as a bell curve, or what's called a Gaussian, named after Gauss, curve. And so if we call this the z-axis, we are going to give it a fancy notation. We're going to say phi of z is equal to a e to the minus z squared over 2. Because we say symmetric, what we mean here is even symmetric. And that means that if you were to replace z with negative z, you would get exactly the same function. And that's going to be important in a few minutes when we talk about certain properties of this bell curve. We threw in a factor of a, and so really, if this is going to be a density, so if phi is a density, what is a? If we were to integrate it over the entire range of our variable, and in this case the Gaussian is defined for all real numbers z. It's a function that just goes out forever and ever and ever. It has horizontal asymptotes of 0, but they just stretch out to infinity. So in this case, when we write something down with infinite limits, we really mean it. So we require the integral of this density or potential density to be 1. And in order to do that, we need to figure out what a is. Now, unfortunately, even though this is what's called a single variable integral, you need multivariable calculus to be able to evaluate it. It turns out here that 2 pi a squared is equal to 1. And because a density function has to be positive, we will take the positive root. So it will turn out that a will need to be 1 over the square root of 2 pi. So as such, we are going to define something called the standard normal density according to the result that we did above. And so we'll define it as phi of z is 1 over the square root of 2 pi e to the minus z squared over 2. Now, if we ever have a continuous random variable that's distributed in this way, we're going to use the following notation. We'll put a capital Z, and we will put n for normal. And for now, we'll put a 0 and 1. And in a moment, I will show you why that is. So we need to know things such as the expectation. So the expectation of this z. Now, as always, expectation is defined in a very standard way. We'll have to integrate z times this density function. And because, as we mentioned, this density function here is even, and z is an odd function, this entire thing is odd. And when we integrate a function, an odd function with symmetric limits, the integral has to go to 0. This is a property that you get from integral calculus. And in particular, we will talk about the integral like this. An integral as t goes to infinity of negative t to t, z over the square root of 2 pi e to the minus z squared over 2 dz. And again, because this is an odd function, this entire limit will end up giving us 0. So the expected value of this standard normal distribution is 0. Now, the variance, as always, is defined as the expected value of z squared minus the expectation of z all squared. Now, we already know that this is 0 from above, so it just remains to evaluate this portion. So again, it's another integral from negative infinity to infinity, but this time we've got a z squared. Now we can write it once again as a limit t goes to infinity, negative t to t of z squared e to the minus z squared over 2 square root 2 pi dz. And unlike before, this entire expression is now an even expression. Other integral properties allow us to write this as limit t going to infinity twice integral 0 to t z squared e to the minus z squared over 2 dz all over the square root of 2 pi. So if you do integrate this by parts, and you're going to need to do it twice, where, for example, u would be z, du would be dz, and because of the nature of the expression up top, this choice of parts will eventually lead you to the result of 1. And this justifies the notation. When we write that our standard variable is distributed as n01, this is the expected value of 0, and this represents the variance. Now we have to be careful. Even though this is the variance, it also equals the standard deviation. The most useful thing about this is the CDF, because the CDF is what we're going to use to get probabilities. So now the CDF we're going to define with a capital phi of z, and just like before, it's going to be an integral from negative infinity to z, and we are going to use the standard normal density with some other dummy variable w. It doesn't really matter what it is. And as always, when we talk about a CDF, it represents the area underneath the density curve from negative infinity up to z. So it's the area under the curve, little phi of z, from negative infinity up to some value z. Now, unlike the exponential distribution, there is no formula for the antiderivative of this standard normal density. So you have to evaluate this CDF numerically or approximately. And when I say numerically, you could use things like Simpson's rule, like you learn about in calculus, or approximately you could use it with a Maclaurin series. So as always, we are going to resort to our friend R. We are going to use the software R. The software R has commands for density functions, so it would be the density, and it also has commands for the CDF. So it would be D norm and P norm. It's going to turn out that you'll use this value here. I should say I'll call it Z. Z for the value you're interested in. The expected value for our standard normal is 0, and the standard deviation and variance are 1. So this is the density, and at the same time, this would be z, 0, and 1 for the area, for the probability function. So for example, if we know we've got some continuous random variable and it's distributed according to the standard normal, we are going to try to rewrite problems in terms of this CDF. So if we were looking for the probability that z is less than or equal to 1.43 with a negative, and this probability is given by that. Now, according to our notation, we are going to use capital Phi of negative 1.43. So this is the CDF for the standard normal. You can easily use something like R to calculate this result, and the command would be p norm negative 1.430 and 1. And running something as simple as that, you'll get a pile of numbers, 0.076358551. So for example, if we are given a question about figuring areas to the right, that isn't going to work for us because we don't have a tool that allows us to calculate areas to the right. We only have a tool that allows us to calculate areas to the left. So since we know the total area underneath the curve is equal to 1 because it's a density property, we can rewrite this as a left area. So it would be the full area, take away the area to the left of 0.23. And again, we're allowed to be sloppy. We don't really care if it's a greater than or equal to or a less than or equal to when it comes to working with continuous distributions. And so if we go ahead and we calculate this, you can use R again, and you'll get something nice like 1 minus p norm 0.2301. And inputting some basic commands like this in R gets you some nice results to whatever default number of decimal places that R likes to use. You can do things that are slightly more involved. So for instance, you could say, let's figure out the probability of negative 1.03, z being between these two values. So then again, it becomes a question of visualizing to understand what your problem is, and then using R to calculate it. In this case, we would simply go the CDF at 2.47 minus the CDF at negative 1.03. Calculating this, we'll end up getting another pile of numbers. If we want to get some intuition about whether or not our numbers are right, we can talk about standard deviations. And so for instance, remember that this normal density is always centered at 0, sorry, and it has a standard deviation of 1. So there's a lot of math that you can do to talk about the shape of this curve. So you can use all the things you've learned in Calc 1 to talk about increase, decrease, concavity, etc. But none of that is really important to us here. Within plus or minus 1 standard deviation of the mean here, it will turn out that we get about 68% of the area underneath this curve. If you're to go out another standard deviation, So if you are within plus or minus 2 standard deviations of the mean, it will turn out that you get about 95% of the area. And if you were to go out one more standard deviation, so to -3 and +3, and if you were to look at the area within there, it will turn out that the vast majority of the area lives within 3 standard deviations. So within plus or minus 3 sigma of the mean, you will get 99.7% of the area. So it gives you a sense. Within 1 standard deviation, you get the majority, but within 2 standard deviations, you get almost all of it. And certainly within 3 standard deviations, the vast, vast majority is contained. So this is the empirical rule for the standard normal.